Okay, chapter 25, Vibrations and Waves. The period of the pendulum depends only on the length of the pendulum and the acceleration of gravity. 25.1. Two pendulums of the same length have the same period regardless of mass. So look at the equation. Mass is not in the equation for the period of a pendulum. So let the math help you. This is a little bit of wave mechanics. In other words, what does a wave look like and what are the parts to it? So you have a wavelength, that's the main thing. That's the distance between two crests or two troughs, or at least the same part of the cycle. And then the amplitude, which is from the midline to the peak. That's the amplitude. And the total height would be 2 amplitude. 25.2, wave description. The back and forth vibratory motion, often called oscillatory motion, of a swinging pendulum is called simple harmonic motion. The pendulum bob filled with sand in figure 25.2 exhibits simple harmonic motion above a conveyor belt. When the conveyor belt is stationary, the sand traces out a straight line. More interestingly, when the conveyor belt is moving at a constant speed, the sand traces out a special curve known as a sine curve. A sine curve is a pictorial representation of a wave. The source of all waves is something that vibrates. Figure 25.4, electrons in the transmitting antenna of a radio station at 960 kilohertz on the AM dial vibrates 960,000 times each second and produce 960 kilohertz radio waves. It's 9.6 times 10 to the 5th seconds per second, hertz. Frequency equals 1 over the period, or the period equals 1 over the frequency. The relationship between period and frequency is they're reciprocals of each other. So it's a hyperbolic relationship. So as one goes up, the other goes down. So frequency equals 1 over period. As period explodes, then frequency tends to 0. Drop a stone in a quiet pond and you'll produce a wave that moves out from the center in an expanding circle as shown in figure 25.6. It is the disturbance that moves, not the water. After the disturbance passes, the water is where it was before the wave passed. When someone speaks to you from across the room, the sound wave is a disturbance in the air that travels across the room. The air molecules themselves do not move along as they would in a wind. The air, like the rope and the water in the previous examples, is the medium through which wave energy travels. The energy transferred by a wave from a vibrating source to a receiver is carried by a disturbance in a medium. Energy is not transferred by matter moving from one place to another within the medium. And here is 25.6, a circular water wave in a still pond moves out from the center in an expanding circle. You can calculate the speed of a wave by multiplying the wavelength by the frequency. For example, if the wavelength is 3 meters and if two crests pass a stationary point each second, then 3 meters times 2 waves pass by in 1 second. The waves, therefore, move at 6 meters per second. In equation form, this relationship is written as V equals lambda F, where V is the speed, lambda, the Greek letter lambda, is the wavelength, and the F is the wave frequency. This relationship holds for all kinds of waves, whether they are water waves, sound waves, radio waves, or light waves, or any other kind of electromagnetic radiation. Figure 25.7, if the wavelength is 1 meter and 1 wavelength per second passes the pole, then the speed of the wave is 1 meter per second. So it's frequency times wavelength equals wave speed. Here are some wave speeds. These are sound. So you see that sound, on average, travels about, at normal room temperature, travels about 340 meters per second. So you can see that the relationship between wavelength and frequency is indirect. So as one goes down, wavelength is going down, 2.13 to 0.64, and frequency is going up. So the relationship is indirect. A person creates a transverse wave, it's kind of like sinusoidal, a transverse wave by shaking the free end of the rope up and down. The arrows represent the motion of the rope. So that's creating like a sinusoidal curve, transverse wave. As we'll see in a bit, we'll see mechanical waves. Longitudinal waves. Not all waves are transverse. Sometimes the particles of the medium move back and forth in the same direction in which the wave travels. When the particles oscillate parallel to or along the direction of the wave, rather than at right angles to it, the wave is longitudinal. Sound waves are longitudinal waves. Both transverse and longitudinal waves can be demonstrated with a loosely coiled spring, as shown in figure 25.9. A transverse wave is demonstrated by shaking the end of the coiled spring up and down. A longitudinal wave is demonstrated by shaking the end of the coiled spring in and out. In this case, we see that the medium vibrates parallel to the direction of the energy transfer. And here is the example of what we're just talking about. You have figure 25.9. You have the transverse and longitudinal waves transfer energy from left to right. A. When the end of the coiled spring is shaken up and down, a transverse wave is produced. When it is shaken in and out, a longitudinal wave is produced. So there are very different waves. Now, we'll look at a little bit more closely to sound waves, which are the longitudinal waves, in the next chapter. But we're still not finished with this chapter. Seismologists. When an earthquake occurs, the sudden release of energy produces waves. Seismologists study and interpret those waves in order to determine the strength and location of the earthquake. They compare the speed, amplitude, and reception of primary longitudinal waves with secondary transverse waves, because they understand how waves travel and the materials through which they pass. Seismologists are able to describe earthquakes, learn about the composition of the earth, and possibly predict future earthquakes. Seismologists conduct research from university and government facilities such as the National Earthquake Information Service, NEIS, in Colorado. Here is 2510, and this is showing constructive interference and destructive interference. So you can see how in A, constructive interference, the waves reinforce each other. They're added to produce a wave of increased amplitude. In destructive interference, the waves cancel each other and no wave is produced. Noise canceling headphones, for instance. When you hear a noise, then you have the microphone or the headphones make another noise that the frequency is shifted, and then the noise is canceled as a result. Figure 2511A, two overlapping water waves produce an interference pattern. B, overlapping concentric circles produce a pictorial representation of an interference pattern. Wave interference is easiest to see in water. Figure 25.11a shows the interference pattern made when two vibrating objects touch the surface of water. The gray spokes are regions where waves cancel each other out. At points along these regions, the waves from the two objects arrive out of step or out of phase with one another. When waves are out of phase, the crest of one wave overlaps the trough of another to produce regions of zero amplitude. The dark and light striped regions are where the waves are in step or in phase with each other. When waves are in phase, the crests of one wave overlap the crests of the other, and the troughs overlap as well. This is figure 25.13. The incident and reflected waves interfere to produce a standing wave. The nodes are places that remain stationary. The nodes would be along the axis line. So you have the node or the null point, and you can examine each wave to see what's in phase, what's out of phase, the incident wave, the reflected wave. The incident wave is the one going away from the student, and the reflected wave is the one that hits the wall and goes back to the student. So then you have the standing wave, of course, which is also very important, and to understand the nodal points. Okay, so good. Next. You can produce a variety of standing waves by shaking the rope at different frequencies. Once you find a frequency that produces a standing wave, doubling or tripling the frequency will also produce a standing wave. A standing wave forms only if half a wavelength or a multiple of half a wavelength fits exactly into the length of the vibrating medium. In figure 25.14a, the rope equals half a wavelength. In figure 25.14b, the rope equals one wavelength. In figure 25.14c, the rope length equals 1 1/2 wavelength. If you keep increasing the frequency, you'll produce more interesting waves. This is a review of figure 2514 we just did. You can produce a variety of standing waves. A, shake the rope until you set up a standing wave of 1/2 wavelength. B, shake with twice the frequency and produce a standing wave of 1 wavelength. C, shake with 3 times the frequency and produce a standing wave of 1 1/2 wavelengths. Figure 25.15, a stationary bug jiggling in still water produces a circular water wave. Figure 25.16, a bug swimming in still water produces a wave pattern that is no longer concentric. 25.9, the Doppler Effect. Imagine a bug jiggling its legs and bobbing up and down in the middle of a quiet puddle, as shown in figure 25.15. Suppose the bug is not going anywhere, but is merely treading water in a fixed position. The crests of the wave it makes are concentric circles, because the wave speed is the same in all directions. If the bug bobs in the water at a constant frequency, the distance between the wave crests, the wave lengths, will be the same for all successive waves. Waves encounter point A as frequently as they encounter point B. This means that the frequency of the wave motion is the same at points A and B and anywhere in the vicinity of the bug. This wave frequency is the same as the bobbing frequency of the bug. Suppose the jiggling bug moves across the water at a speed less than the wave speed. In effect, the bug chases part of the crests it has produced. The wave pattern is distorted and is no longer concentric as shown in figure 25.16. The center of the outer crest was made when the bug was at the center of that circle. The center of the next smaller crest was made when the bug was at the center of that circle, and so forth. The centers of the circular crests move in the direction of the swimming bug. Although the bug maintains the same bobbing frequency as before, an observer at B would encounter the crest more often. The observer would encounter a higher frequency. That is because each successive crest has a shorter distance to travel, so they arrive at B more frequently than if the bug were not moving toward B. An observer at A, on the other hand, encounters a lower frequency because the longer time between the wave crest arrivals. To reach A, each crest has to travel farther than the one ahead of it due to the bug's motion. As a wave source approaches, an observer encounters waves with a higher frequency. As the wave source moves away, an observer encounters waves with a lower frequency. This apparent change in frequency due to the motion of the source or receiver is called the Doppler effect, after the Austrian scientist Christian Doppler. The greater the speed of the source, the greater will be the Doppler effect. Water waves spread out over the flat surface of the water. Sound and light waves, on the other hand, travel in three-dimensional spaces in all directions, like an expanding balloon. Just as circular wave crests are closer together in front of the swimming bug, spherical sound or light wave crests ahead of a moving source are closer together than those behind the source and encounter a receiver more frequently. Figure 25.17, the pitch of sound is higher when the source moves towards you and lower when the source moves away. And again, this change of frequency is called the Doppler effect, this change of frequency. In figure 25.18, the police calculate a car's speed by measuring the Doppler effect of radar waves. Also, you have Doppler weather radar, which helps to determine the speed of storms. It's very easy. It's a wonderful tool. Long-range forecasts would be impossible without Doppler radar. Light. The Doppler effect also occurs for light. When a light source approaches, there is an increase in its measured frequency. And when it recedes, there is a decrease in its frequency. An increase in frequency is called a blue shift because the increase is towards the higher frequency or the blue end of the color spectrum. A decrease in frequency is called a red shift, referring to the low frequency or red end of the color spectrum. Distant galaxies, for example, show a red shift in the light they emit. A measurement of this shift enables astronomers to calculate their speed of recession. A rapidly spinning star shows a red shift on the side turning away from us and a blue shift on the side turning towards us. This enables a calculation of the star's spin rate. Here is a figure, two figures, 25.19, a bug swimming at the wave speed keeps up with the wave crest it produces. But in 25.20, the bug swimming faster than the wave speed produces a wave pattern in which the wave crests overlap at the edges. So it's traveling faster than the wave it is producing. We're going to be relating this to sonic booms. Here we have four patterns. The wave patterns made by a bug swimming at successively greater speed change, overlapping at the edges, occurs only when the source travels faster than the wave speed. So we have v for velocity, less than v of the wave, v equals the v of the wave, v is greater than the v of the wave, and v is much greater than the velocity of the wave. And that is figure 25.21. A speedboat knifing through the water generates a two-dimensional bow wave. A supersonic aircraft similarly generates a shock wave. A shock wave is a three-dimensional wave that consists of overlapping spheres that form a cone. A shock wave occurs when an object moves faster than the speed of sound, just as the bow waves of a speedboat spreads until it reaches the shore of the lake. The conical shock wave generated by a supersonic aircraft spreads until it reaches the ground, as shown in figure 25.22. The bow wave of a speedboat that passes by can splash and douse you if you are at the water's edge. In a sense, you can say that you are hit by a water boom. In the same way, a conical shell of compressed air sweeps behind the supersonic aircraft. The sharp crack heard when the shock wave that sweeps behind a supersonic aircraft reaches the listeners is called a sonic boom. We don't hear a sonic boom from a slower than sound or subsonic aircraft because the sound wave crests reach our ears one at a time and are perceived as a continuous tone. Only when the aircraft moves faster than sound do the crests overlap and encounter the listener in a single burst. The sudden increase in pressure has much the same effect as the sudden expansion of air produced by an explosion. Both processes direct a burst of high pressure air to the listener. The ear cannot distinguish between the high pressure from an explosion and the high pressure from major overlapping wave crests. Here's that cone again from the supersonic aircraft, figure 25.22. It says a shock wave is swept continuously behind a supersonic aircraft. You can look at that and understand that it's conical, it's three-dimensional. It's a cone. Watch for the advent of newly designed aircraft that fly 1.8 times the speed of sound and produce sonic booms only 1/100th the strength of the supersonic Concorde, which was grounded following a fatal accident in 2000. A common misconception is that sonic booms are produced at the moment that an aircraft flies through the sound barrier. That is, just as the aircraft surpasses the speed of sound. This is equivalent to saying that a boat produces a bow wave only when it first overtakes its own waves. This is not so. The fact is that a shock wave and its resulting sonic boom are swept continuously behind an aircraft, traveling faster than sound, just as the bow wave is swept continuously behind a speedboat. In figure 25.23, listener B is in the process of hearing the sonic boom. Listener A has already heard it, and listener C will hear it shortly. The aircraft that generated this shock wave may have broken through the sound barrier hours ago. It is not necessary that the moving source emits sound for it to produce a shock wave. Once an object is moving faster than the speed of sound, it will make sound. A supersonic bullet passing overhead produces a crack, which is a small sonic boom. If the bullet were larger and disturbed more air in its path, the crack would be more boom-like. When a lion tamer cracks a circus whip, the crack sound is actually a sonic boom produced by the tip of the whip when it travels faster than the speed of sound. Snap a towel, and the end can exceed the speed of sound and produce a mini sonic boom. The bullet, the whip, and towel are not in themselves sound sources, but when traveling at supersonic speeds, they produce their own sound as waves of air are generated to the sides of the moving objects.